Jan Calais from the Rochester Institute of Technology in New York shared an observation that resonates deeply within the scientific community. We had an idea of what galaxies would look like at these distances and how much detail we could see, but I think the reality far exceeds our imagination and really blows us away. Imagine looking into the cosmic nursery and seeing something there that shouldn't even exist. This sentiment encapsulates the awe and surprise many astronomers felt when the James Webb Space Telescope, JWST, began transmitting its first images. These images not only shattered expectations but also challenged the very foundations of modern cosmological theories. As Calais put it, we are now at the beginning of a new scientific era, and nobody knows at the moment where this journey will go. Only one thing is certain: the latest findings are groundbreaking, staggering, and will change our understanding of the universe forever. The James Webb Space Telescope, or JWST for short, is a $10 billion technological marvel that surpasses the Hubble Space Telescope in both range and image sharpness by a wide margin. Since its launch in December 2021 and its operational start in the summer of 2022, JWST has provided us with breathtaking images of the early universe, distant cosmic nebulae, menacing black holes, and even planets within our own solar system. With its 18 hexagonal mirrors arranged in a honeycomb-like structure and its unique infrared technology, JWST is the most extraordinary telescope humanity has ever built. As Calais noted, it sounds crazy, but this telescope was the hope of many thousands of astronomers on this Earth. They eagerly awaited its launch, knowing that the telescope's new capabilities would soon show them things they had dreamed of all their lives. They counted on the truth, on the confirmation of ideas that had long been only theories on paper. However, the results JWST produced were not what many astronomers had anticipated. The telescope, after being safely placed in space, directed its mirrors for over 72 hours at a seemingly empty region of the cosmos. From our vantage point on Earth, this area appears devoid of stars or nearby galaxies. Yet, JWST's extraordinary sensitivity allowed it to capture the faintest, oldest light signals from the universe, light that has been traveling for 13.5 billion years or more. In the image JWST produced, these ancient signals manifest as blurry red specks of light, with orange, yellow, and blue hues representing increasingly closer light sources. This image, showing predominantly the light of very old galaxies, sent shockwaves through the scientific community. "These galaxies shake science," Calais remarked, echoing the sentiments of many of his peers. The discovery of these ancient galaxies was not a cause for celebration for all scientists. Many had hoped that the data would confirm long-held theories and provide a clear picture of the universe's early history. Instead, the findings presented a challenge to the established cosmological worldview. The shock was compounded when, shortly after the image was published, Indian-American researcher Rohan Naidu identified a galaxy that existed just 300 million years after the Big Bang. This discovery was not an isolated case. Naidu and his team, along with other international research groups, found one ancient galaxy after another. The sheer number of these discoveries led to a realization: something was amiss with the Big Bang theory and our understanding of the universe's early history. The magic of this discovery, Calais noted, was that many dedicated young researchers felt encouraged to think differently, to keep searching for even older galaxies, and to believe possible what conservative research had long rejected. New theories began to emerge, and some older models of the universe that had previously been overlooked were suddenly gaining attention. The JWST, in a sense, had disappointed those who had hoped everything would remain the same. For those who had long suspected that the Big Bang theory might not fully align with the findings of modern quantum physics, the new discoveries were a form of validation. They continued to search for the truth about the origin and nature of our universe, without relying solely on established theories. This development, while surprising, was not entirely unforeseeable. One of the Hubble Space Telescope's last great discoveries was GN-Z11, a galaxy that existed at a redshift of 11.6, about 420 million years after the Big Bang. Even then, some scientists began to question the validity of older cosmological conceptions. However, GN-Z11 was a single case and could be explained within the existing framework. The JWST's discoveries, on the other hand, were more numerous and presented a greater challenge. The concept of redshift is crucial in understanding these discoveries. Redshift measures how much the light from a galaxy has been stretched as the universe expands. The higher the redshift, the further back in time we are observing a galaxy. The galaxies first discovered by Naidu and his team had a redshift of 13, meaning they existed about 300 million years after the Big Bang. Later, even more ancient galaxies were found with redshifts as high as 20. Conservative scientists have been cautious about these findings, noting that the redshifts have not yet been confirmed and it is not definitively proven that the light signals are from galaxies. Nonetheless, the light is undeniably ancient, and if it was not emitted by galaxies, it raises the question, where did it come from? One common method to detect and determine very old objects in space is through gravitational lensing, a phenomenon where the gravity of a massive object, like a galaxy cluster, bends the light from objects behind it, magnifying them. Astronomers led by Xin Yen of the University of Missouri-Columbia used this technique to find 88 candidate galaxies beyond a redshift of 11. Yan's team even discovered a galaxy with an incredible redshift value of 20. If confirmed, these would be the most distant galaxies ever discovered. High redshift galaxies were also discovered in two other studies that did not use gravitational lensing. These findings were part of the Cosmic Evolution Early Release Science (SOURCE) study, which used JWST's near-infrared camera (NIRCam) and near-infrared spectrograph (NIRSpec) to analyze deep space images. Additional data on these presumed galaxies were obtained using the mid-infrared instrument (MIRI) camera. Astronomers at the University of Edinburgh employed a similar approach to discover a galaxy candidate with a redshift of 16.7, meaning it existed just 250 million years after the Big Bang. Another team, led by Stephen Finkelstein of the University of Texas at Austin, used the SOURCE method to discover a galaxy with a redshift of 14.3, placing it 280 million years after the Big Bang. This galaxy has since become known as Macy's Galaxy, named by Finkelstein as a birthday present for his daughter Macy. Despite these exciting discoveries, it is important to note that these galaxies are not yet confirmed because we cannot see them clearly. Our current technology relies on analyzing the light spectrum and using computer algorithms to estimate the size, density, mass, and number of stars in these objects. However, this does not definitively prove that the light was emitted by galaxies. It could have come from other sources, such as ultra-supermassive black holes. If these black holes were indeed the source of the light, it would raise even more questions about the early universe. How could such gigantic black holes have existed so soon after the Big Bang? Regardless of the source of the light, one thing is clear: these discoveries are rewriting our understanding of the cosmos. The presence of these distant galaxies also provides evidence of significant ultraviolet light emission. This suggests that these galaxies played a role in the ionization of hydrogen gas, which according to previous cosmological models, ended the so-called cosmic dark ages. During this period, the universe was dark, with no light until the first stars began to shine. The Edinburgh team's research calculated the ultraviolet luminosity of candidate galaxies between redshifts 8 and 15, concluding that there was enough ultraviolet radiation emitted by stars in these early galaxies to ionize the universe. These newly discovered high redshift galaxies likely existed on the cusp of the universe becoming filled with light. Unlike today's galaxies, which can host hundreds of billions of stars, these early galaxies were probably only a few thousand light-years across and contained only tens of millions of stars. According to experts from Scotland, these galaxies represent a generation that formed shortly after the first galaxies and are still in their infancy. The abundance of high redshift galaxies discovered by JWST, as well as the amount of ultraviolet light shifted to longer infrared wavelengths, further suggests that galaxies were more numerous in the early universe than previously thought. This would be a completely new finding, but it does not necessarily overthrow the Big Bang theory. Instead, we may need to revise our assumptions about the duration of the dark ages and the formation of the first stars and galaxies. According to Finkelstein's team, our cosmos was already shining brightly with many small galaxies less than 300 million years after the Big Bang. However, these findings are not without controversy. Other researchers have found very old galaxies in JWST images that appear much larger and more massive than expected. Their luminosity may have matched that of present-day galaxies, suggesting that the first galaxies, if they were indeed the first, must have been true starbursters, forming many very bright and short-lived giant stars. The existence of these early star giants had already been computationally predicted, but researchers had not previously assumed that these stars were organized into galaxies. Astronomer René Soares of the University of California, Santa Cruz, compared Hubble and Webb photographs of the same galaxies taken around cosmic noon. Most large galaxies appear significantly smaller in the infrared wavelengths measured by Webb than in Hubble's photos. According to Soares, Hubble's studies suggested that galaxies start small and expand over time. However, the Webb results imply that Hubble may have missed critical details, indicating that galaxy evolution could be more complex than previously understood. These findings challenge the notion that galaxies follow a straightforward path of growth and expansion. Instead, they suggest a more intricate process, where early galaxies might have experienced rapid, intense periods of star formation, followed by periods of stagnation or even contraction. This complexity has led to renewed debates within the scientific community. Some researchers argue that we need to reconsider our models of galaxy formation and evolution. Others propose that we might be witnessing the effects of unknown physical processes or even entirely new phenomena that have yet to be fully understood. The discovery of these high-redshift galaxies has opened up a new frontier in cosmology, one that may require us to rethink not just the timeline of cosmic events but also the fundamental forces and interactions that shaped the early universe. JWST's revelations are reshaping our view of the universe. By uncovering ancient galaxies, it challenges old theories and paves the way for new discoveries. We stand on the brink of a transformative era in astronomy.